Hi boys and girls, today we begin our Unit 8 lectures, which comprise the AP Calculus AB exam review. In Lecture 8.1, our review topic is Area Between Two Curves. We'll briefly review the topic and then work through a few free response examples. The area between two curves can be found by evaluating the following integral: f of x minus g of x dx from a to b. And that's referring to this diagram, y equals f of x, y equals g of x on the interval from a to b. Remember, the function on top is listed first in the integrand, and a sketch is always helpful in determining which function curve is on top of the other. When finding the area between a function curve and the x-axis is the second function curve with the equation g of x equals 0. So technically, if we wanted to find the area under this curve f of x, we could list this as f of x minus g of x. But since the function g of x is just the equation g of x equals 0, then when finding the area between a function curve and the x-axis, we simply need to evaluate the integral f of x d of x on the specified interval, in this case from 0 to 2. Now let's do an example. Here are the steps we'll need to go through to find the area between y equals the square root of x and y equals x squared. First, we'll sketch the curves if a sketch is not already provided. Then we'll determine the endpoints of integration by solving for the points of intersection between the two curves. Third, we'll set up the integral correctly, and fourth, we'll evaluate the integral to find the area. Since a sketch is already provided, let's find the endpoints of integration by solving for the points of intersection between the two curves. Therefore, I will set these two curves equal to each other to see where they intersect. Let's square both sides. This gives me x equals x to the fourth. And when I subtract the x over and set the equation equal to 0, I'm able to factor out an x, and I'm left with difference of cubes, which does factor further. X minus 1, x squared plus x plus 1. And now that this is fully factored, I can see that I have points of intersection at 0 and at 1. Now from this graph you can clearly see that those are the points of intersection, but just to be certain, make sure that you provide some analysis to determine what the points of intersection are. Now let's set up the integral correctly. We're going to integrate from 0 to 1, and the function on top is the square root of x, which I'll write as x to the 1/2, minus x squared dx. This becomes 2/3 x to the 3/2 minus 1/3 x cubed from 0 to 1. When I put 1 in for x, I get 2/3 minus 1/3. And since putting 0 in for x here doesn't give us any further calculation, my answer is 1/3. That's the area between these two curves. Let's find the area between y equals 4x plus 16 and y equals 2x squared plus 10 on the interval from -2 to 5. You can see in this example the curve on top changes throughout the interval, so a sketch is definitely needed in order to set up the integral correctly. From a to b, the quadratic is on top of the line, but from b to c, the line is on top of the quadratic, but then from c to d, the quadratic is once again on top of the line. So we know, of course, that the very beginning of the interval is -2 and the end is 5, but we do need to find these points of intersection between the two curves. We can see what they are from this particular graph, but we can't take anything for granted. So let's set 4x plus 16 equal to 2x squared plus 10 and solve for the points of intersection. If I set this equal to 0, I'm going to have 2x squared minus 4x minus 6. I can divide both sides by 2 and get x squared minus 2x minus 3. When I factor that quadratic, x minus 3 x plus 1, I see there are 2 points of intersection at 3 and at -1. So in this case, A is -2, B is -1, C is 3, and D is 5. And when we set up our integral, we're going to have the following. From -2 to -1, 2x squared plus 10 minus 4x plus 16. Of course, integrated with respect to x. Then we're going to add to that from -1 to 3, 4x plus 16 minus 2x squared plus 10. Again, integrated with respect to x. And then we'll add to that our final integral, which will be from 3 to 5. And once again, we're going to have 2x squared plus 10 minus 4x plus 16 integrated with respect to x. Now let's combine like terms in the integrands. In the first integral, we'll have -2 to -1, 2x squared minus 4x minus 6 dx. In the second integral, from -1 to 3, we'll have -2x squared plus 4x plus 6 dx. And in the third integral, from 3 to 5, we'll have 2x squared minus 4x minus 6. When we integrate, we'll end up with 2/3 x cubed minus 2x squared minus 6x from -2 to -1. We're going to add to that a -2/3 x cubed plus 2x squared plus 6x from -1 to 3. And then we'll add to that 2/3 x cubed minus 2x squared minus 6x from 3 to 5. When all of this is calculated, the area between those two curves on the interval from -2 to 5 is 142/3. In this example, we're going to find the area between y squared equals 2x plus 6 and y equals x minus 1. Here we have the curve y squared equals 2x plus 6, and here is the line y equals x minus 1. Let's write y squared equals 2x plus 6 as the two functions f of x equals the positive square root of 2x plus 6 and g of x equals the negative square root of 2x plus 6. Then our third function will be h of x equals x minus 1. So the top half of the sideways parabola will be f of x, the square root of 2x plus 6. The bottom half of the sideways parabola will be g of x, negative square root of 2x plus 6, and h of x will be the line x minus 1. In the sketch, we see that f of x and g of x enclose the area to the left of the vertical line x equals -1, and f of x and h of x enclose the area to the right of the vertical line x equals -1. This means we'll need to set up two integrals. The first one will be from A, the x-intercept of this curve, to -1 of f of x minus g of x, the top half of the sideways parabola minus the bottom half of the sideways parabola. We'll add to that the integral from -1 to b, this point of intersection between the two curves, of f of x minus h of x, the top half of the sideways parabola minus the line. So let's find these points of intersection and the x-intercept of this curve. We can find the x-intercept of this curve by letting y equal 0. 0 is equal to 2x plus 6. That means -6 is equal to 2x, and x is equal to -3. That's the x-intercept of this curve, and that will be a in the integrand. Now we can find the point of intersection between the two curves by setting them equal to each other. This will be easiest to do if we square this function. Y squared is equal to x minus 1 quantity squared. Now we can say that x minus 1 quantity squared is equal to 2x plus 6. And when we square this binomial, we get x squared minus 2x plus 1. 0 then will be x squared minus 4x minus 5. And when we factor this quadratic, x minus 5, x plus 1, we find 2 points of intersection at 5 and at -1. Therefore, the points of intersection between the two curves occur at -1 and at 5. Now let's set up the integrals. The first integral from -3 to -1. The top curve, the square root of 2x plus 6, minus the bottom curve, the negative square root of 2x plus 6. Integrated, of course, with respect to x. Then we'll add to that a second integral from -1 to 5. The top curve is the positive square root of 2x plus 6. The bottom curve is the line x minus 1. Again, integrated, of course, with respect to x. When we simplify these integrands, we'll have -3 to -1 of 2 square root of 2x plus 6 dx plus the integral from -1 to 5 of the square root of 2x plus 6 minus x plus 1 dx. When we integrate, we'll get 2/3 2x plus 6 to the 3/2 power, evaluated from -3 to -1, plus 1/3 2x plus 6 to the 3/2, minus 1/2 x squared plus x, evaluated from -1 to 5. And when all calculations are done, the value of this integral and the area between those two curves is 18. Now, let's find the area of this same region by integrating with respect to y. This means we'll need to rewrite the functions in terms of y and use endpoints of integration on the y-axis. In setting up the integral, the function to the right goes first. Right function minus left function. But notice for this region, the right function minus the left function gives us this entire area. Therefore, we're only going to need one integral, f of y minus g of y from c to d. So let's rewrite these functions in terms of y. When I add 1, I get y plus 1 is equal to x. That means f of y is equal to y plus 1. Y squared minus 6 is equal to 2x, and when I divide by 2, I get 1/2 y squared minus 3 is equal to x. Therefore, g of y is equal to 1/2 y squared minus 3. Now the endpoints of integration are going to be the y values of these points of intersection, which are -2 and 4. So in setting up this integral, -2 to 4 of the right function, which is y plus 1, minus the left function, which is 1/2 y squared minus 3. And in this case, we're integrating with respect to y. Let's simplify this integrand. -2 to 4, -1/2 y squared plus y plus 4 dy. When we integrate, we'll get -1/6 y cubed plus 1/2 y squared plus 4y from -2 to 4. And when we evaluate, we get an area of 18. Here we have a free response question from the 2007 AP exam. Let R be the region bounded by the graph of y equals e to the 2x minus x squared and the horizontal line y equals 2. So that's this region. And let S be the region bounded by the graph of y equals e to the 2x minus x squared and the horizontal lines y equals 1 and y equals 2 as shown above. So that's this region. We're asked to find the area of R and find the area of S. Now this is on the calculator allowed section of the exam, so we're going to let the calculator do the heavy lifting. For the first integral, we'll simply need to take the curve and subtract the horizontal line y equals 2 to get that area. We will need the endpoints of integration, which will be the points of intersection between the two curves. When we set these two functions equal to each other, we can find those points of intersection, but we'll have to use our calculators. We can either use the equation solver function on our calculator, or we can graph both of these curves, y equals e to the 2x minus x squared and y equals 2, and use the intersect function to find the points of intersection. The 2 points of intersection are 0.446 and 1.554. I'm going to label the lower endpoint A and the upper endpoint B just to make it easier to write my integral. So the first integral will be from A to B, e to the 2x minus x squared minus 2 dx. Using the integrate function in your calculator, the value of this integral and the area of that region is 0.514. As long as you show that you found your endpoints of integration by setting the equations equal to each other and the setup of your integrand, you can use your calculator to find the value of that integral. Now let's do letter B. We're asked to find the area of S, and the easiest way to do that would be to find the area of R plus S by taking the curve and subtracting the horizontal line y equals 1, and then subtracting from that area the area of R, which we found in letter A. We will need the endpoints of integration, which are the points of intersection between the curve and the horizontal line y equals 1. We'll find that by setting the curve equal to 1 and use your calculator to find the points of intersection 0 and 2. So for letter B, we'll have the integral from 0 to 2 of the curve e to the 2x minus x squared minus 1 dx. And then the value of this integral minus 0.514 will eventually be our answer. Using your integrate function on the calculator and subtracting 0.514 gives you a value of the integral 1.546. Here are the scoring guidelines for that question. We did letters A and B, and here are the points assigned for those two parts. For letter A, 1 point was given for the setup of the integrand, 1 point was given for limits, those are the endpoints of integration, and how we found them, and then a 3rd point was given for the correct answer. For letter B, 1 point, again, for the setup of the integrand. Notice they subtract off the area of R. Another point for the limits of integration, which are 0 to 2, and then a 3rd point for the correct answer. Here's an alternate method of finding that answer. Here's one more free response question from the 2009 AP exam. Notice this is on the section of the exam where no calculator is allowed. Let R be the region bounded by the graphs of y equals the square root of x and y equals x over 2 as shown in the figure above. Find the area of R. So we're going to take the curve y equals the square root of x and subtract the line y equals x over 2 in the integrand. In this problem, we're given the points of intersection between the two curves, so we know what the endpoints of integration are. The integral will be from 0 to 4, the square root of x, which I'll write as x to the 1/2, minus x over 2, which I'll write as 1/2 x, and of course we're integrating with respect to x. This will be 2/3 x to the 3/2 minus 1/4 x squared, evaluated from 0 to 4. 2/3 times 4 to the 3/2 minus 1/4 times 4 squared, and plugging the lower endpoint of integration in gives us a 0 value. So this is going to be 16/3 minus 4, which is 4/3. Therefore, the area between those two curves is 4/3. Here are the scoring guidelines for that question. We did letter A, and here are the points assigned for that part of the question. 1 point for the integrand, another for the antiderivative, and a third for the correct answer. Tip number 1 for the AP Calculus AB exam: show all work. Remember that the grader is not really interested in finding out the answer to the problem. The grader is interested in seeing if you know how to solve the problem. And common student error number 1. Often a student will make the mistake of thinking that if the second derivative at a certain value is 0, then that point is a point of inflection, but that is not necessarily the case. You must show that concavity changes on either side of that point to verify that it is indeed a point of inflection. That's it for today's lecture. Keep calm and do calculus. God bless you, boys and girls.